Hi, thanks for tuning in. Today I'm going to be talking about our recent work on learning where to trust unreliable models for deformable object manipulation. So just to motivate, even the study of deformable objects, is sometimes difficult for people who aren't in this field. So I want to start with this question: why work on deformable object manipulation? And it's easy to think about a lot of different applications, domestic, industrial, even surgical applications for manipulating deformable objects. And those are great, but really I feel like when we focus on deformable objects, we have an opportunity to not just enable cool applications, but also to challenge the fundamental assumptions that have guided robotics so far. So what do I mean by that? Well, these are assumptions like rigidity, known dynamics models, having very simple uncertainty distributions, having fully actuated systems. Using these assumptions has allowed robotics to make fantastic progress on rigid body manipulation. But actually, these assumptions will hold us back if we try to generalize beyond that. So we need to start challenging some of these and making sure that our methods are not depending so much on them. So that's why I think of deformable object manipulation as robotics complete, meaning that if we can enable deformable object manipulation tasks in a robust and general way, then we will actually have solved many of the most difficult problems in robotics. So a lot of what I'm going to talk about today relates to modeling of deformable objects and using those models within a motion planner. But I just want to give a little background to say that the topic of modeling deformable objects is very, very well studied from at least the 90s, probably even earlier. I've just highlighted a few publications that model deformable objects in different ways using mass spring models or FEM or meshless models. A lot of great work has been done. However, what we're trying to do is get away from manually defining these models because they can be quite complex. They have different kinds of numerical sensitivities. And in general, we're not going to have these a priori for a new object that we encounter. Now, that hasn't stopped people from doing motion planning for deformable objects, and a lot of great work has been done in that area, including what you see here. And again, I want to emphasize that although these planners have produced impressive results, they're still fundamentally limited by the accuracy of their models, right? Assuming that the model is always accurate is only going to get you so far when you're dealing with a complicated object that perhaps you haven't seen before quite in that form. Now, another branch of work looks at this as a control problem and basically seeks to online produce motions for manipulating a deformable object to make it kind of locally deform in a certain fashion to locally satisfy some task requirement. And there we see adaptive models, actually, and learned models as well, that are being used to quickly adapt a rather simplified model to the current situation. So just a linear model in the case of the above two. Or we can use prior learning to have a quick way to look at what we should do in a given situation. And these are all very interesting models and definitely can enable certain applications, but the ability to plan long horizon with these is quite limited. So we really can only do things locally with these kinds of assumptions. So before I get into the main part of the talk, I wanted to do a little bit of a teaser here for some recent work that came out at ICRA, which relates to perception. Now, this is actually tied very closely to the modeling aspect of this, because whatever model you pick, you still need perception to figure out what is the state given those model parameters. So this was work by Yishuan Wang, who's now a PhD student at UIUC, and Dale McConaughey, who is now a researcher at TRI. And what they were doing here was to basically find a way to track deformable objects given very severe occlusion. And it turns out this is very tricky using existing methods because they assume all sorts of priors on the way the object behaves that rely on basically being able to see the object at all times, or at least see a vast majority of the object. And here we really wanted to get away from that. And so we're tracking here, you see a rope, despite very severe occlusions. Now we're actually tracking the rope and preserving the topology of it in terms of intersections. So the rope won't pop through itself, a very common problem with these CVD-based trackers. So we've managed to address that. We don't just do rope, we also do cloth. So you can see the cloth is going to rest on the cylinder without penetrating through it. Of course, the model of the cylinder is known, but still, we're able to track among obstacles with contacts and prevent self-penetration or crossing, which is, in my view, a really big step forward for these tracking methods. So please go check that out if you need a deformable object tracker. The code is available for free online at the address below. Okay, so getting back to the main topic of this presentation, which is what do we do when we don't have great high fidelity models, right? What do we do when our models are unreliable? Well, we've been looking at this question for a number of years, and I'll just say a few of the things we did very briefly here before getting to the main component. So at first we said, okay, well, we don't know when our dynamics models are reliable, so let's have a whole library of models and switch between them online to do control, right? This works fine when you are trying to do things locally, again, for control purposes. We also said, well, can we make a simplified model and a model that doesn't try to represent all the geometry of the object because it could be very complex. Imagine a crumpled up shirt, for instance. It's very difficult to actually simulate that. So instead, what we actually care about are what we call constraint boundary interactions. So can we have a model that's sufficient to predict when we're about to overstretch an object or when that object kind of catches on an obstacle? Because if we can, then we can enable motion planning in complex environments that will basically avoid violating those constraints without knowing the true shape of it. So we had a whole branch of work on that. And more recently, we're looking at the problem in a different way and saying, well, look, every model we come up with is going to make mistakes, right? It's going to be inaccurate somewhere. What can we do to exploit the beneficial aspects of the model, right? The parts where it is accurate, where it does predict well, while actually learning to avoid the parts of state space where that model is not reliable. So that's the focus of what I'm going to talk about today. We're going to be learning to avoid a model's mistakes, or in general, where the model can't be trusted. Okay, so this is the work of my PhD student, Peter Mitrano, in collaboration with Dale. And the key questions that we were looking at in this paper that just recently came out in Science Robotics was, how do we learn a dynamics model for complex deformable object tasks? Usually, we kind of take a version of the task and we try to do things with the deformable object in that environment. So for instance, we might have an environment, you'll see here, where we have a car engine bay and we're trying to move a hose around there. So traditionally, we would take the whole environment and the whole deformable object, and we would basically put them into a simulator, and we would try many different motions in there, maybe millions of motions, and try to learn a model of the dynamics for that environment. We tried that, and that does not work for the complexity of tasks that we were looking at. So instead, what we did is we simplified the problem. We said, okay, let's try to learn the dynamics of the rope in isolation, basically when there are no obstacles around. And when we don't have to worry about the kinematics of the robot, we can have just free-flying grippers and learn that dynamics model. And then we know that that dynamics model is not going to predict well when the rope is doing complex obstacle interactions. Sometimes when the rope is dragging on obstacles, it actually does work okay to use that dynamics model, but sometimes it doesn't. And so then we want to figure out, when is that model that we learned in the simplified scenario going to be reliable in the true constrained environment, more complex. We further said, well, okay, what do we do if if the state of the rope is basically not in the reliable part of the model space? We're just given a starting state where the rope prediction is the model's prediction is unreliable. Well, to that end, we developed what we call a recovery procedure to move back to the part of state space where our model is reliable. Okay, so I'll be talking about these in a lot more detail next. This is our overall framework. As you can see in the upper left, it starts with learning the dynamics of the rope in a simplified scenario. And then in the lower left, we are going to train a classifier, which is going to predict when we are going to be in, when our model's prediction is trustworthy. We're also going to train the recovery procedure based on the classifier. And then once we've got these classifier and recovery procedures, we can do part C on the right here, which is going to execute, sense the state, and replan when the robot gets stuck, meaning when we enter a part of space where we can't make progress on our trajectory anymore. We'll recover and we'll continue execution until we complete the task. Okay, so just to motivate this a little bit further, here's an example where doing the traditional dynamics learning of just, doing the learning directly in the space, in the range of tasks that we're trying to achieve is very difficult. So you see a cluttered tabletop scenario, you see the rope moving there. We did our best to try to learn the dynamics of the rope in these scenarios. But as you can see, they're very complex when the rope starts catching on things and sliding, even crossing itself. And to this day, we are not able to learn a good dynamics model in these scenarios, despite all the things we've tried. So instead, we move to a simplified scenario. So this is what we are actually doing for our method. We're translating grippers in the workspace that are kind of free floating, and we're observing the rope state as we do that. And it turns out that learning these dynamics is actually quite straightforward, and we can do it with a fairly small neural network. And of course, in simulation here, we have access to lots and lots of data. So we have as much data as we want. Okay, so we collect the data by rolling out random trajectories in this unconstrained environment. And once we have that data, we train the neural network you see on the right, which is really just two fully connected layers. They're fairly wide, but it's a very simple architecture. And it's this residual architecture where we're just adding a prediction of the model plus the current state to get the next state. And it turns out this is very straightforward to learn. So great, that gives us this baseline unconstrained dynamics. Now we move on to training the classifier. So now we need another data set, but we have a much smaller data requirement here. We don't need millions and millions of data points. I believe this works with about 50,000 trajectory steps, which is not too laborious to collect and actually could be done in the real world. It would probably take a few days of data collection, definitely not months. So we can collect this kind of data set, and given that data set, we can label the data not based on some kind of regression metric, but instead, what we can do is label the data based on how well our prediction, the prediction of our learned model, corresponds with what actually happened. And so if we correspond well with what we predicted, then we give it a label of 1, meaning the model we learned is accurate here. If it doesn't correspond well, we label it 0, and then after that, the predictions diverge and we kind of throw out data. Given all of this data, we can learn a classifier which predicts the model reliability for a given state and action. Now, part of learning this classifier requires knowing about the local environment, the environment around the rope. And so we actually give that to the classifier as a voxel grid, and we process that with some convolutions before it's put into this big fully connected layer here. And again, only two fully connected layers here. So again, not a very complex network structure here to learn this model, to learn this classifier. Now, let's say we learned a classifier, but we happen to be in a state where the classifier says everything you try, every action you try in this state, we don't have a reliable prediction. Well, then the robot would be stuck, right? So here's an example of a state like this, where the rope is resting on an obstacle, but we've never seen anything like this in training our dynamics model. So what can we do? Well, we need to basically check a bunch of actions to see, will our classifier allow us to move in any direction? Right? Will it be accurate enough in any given any action from this state? If the classifier is rejecting all these actions, we need a way to recover. So how do we do that? Well, we need to learn a method to do this recovery. And what we're trying to do is not basically learn a better prediction, because we don't have the data for that. What we are actually trying to do is to move in a way that we can get to a part of state space where the model can be trusted again. Now, how do we learn how to do that? Well, it turns out in the data set that we collected to train the classifier, there are examples where the classifier is not able to predict what is going to happen given an action, but anyway, the robot did some action, and that led it to a state where the classifier was able to predict the outcome of at least a few actions. Right? So we can look for examples in the data like that once we've learned our classifier, and then we can use those examples to train a recovery method that basically predicts the probability of recovery for a given state and action. So if I'm in this state and I plan action, how likely is it that the resulting state will be one that I can use my learned model? And so here's how that looks. Once we've learned the recovery, we start to execute it. And as we see, just after one step, we're still not recovered, so we execute it for another step. And that gives us a state where recovery is successful, meaning that we get to a part of state space where a model prediction is good enough. And then we can just plan to get to the goal. So we're not going to be trapped by these states where we're not able to predict. And finally, we put this all into a planning and execution framework. Here's basically how it works. We use a kinodynamic ROT with the learn dynamics function that we learned, and we use the classifier to reject transitions in the RT where the dynamics model is deemed to be unreliable. And if we get stuck, meaning that we can't generate any actions that the classifier says are going to be reliable, then we apply the recovery procedure. So here's how it looks. First, we apply the recovery. It was really fast then we plan to get to the goal. Okay. We tested this framework first in simulation and got some statistical results there. And then we also did a few demos in the real world. So we tested on environments, basically involving dragging a rope and two arms manipulating a rope. And we compared two baselines, including learning the full dynamics, this kind of the default method, try to learn everything. And we also compared to ablations of our method. The metric we use for success here is basically being within a certain distance to the goal. Here's it's 5 centimeters, and we give it 3 minutes of planning and execution time. So execution time does count against the time. So here's what we got in the rope dragging example here. And the idea here is that we're dragging a rope with this gripper, and we're trying to put this end of the rope in some target location. So we can't control the end of the rope directly. We have to drag it among these obstacles. And we saw here that if we try to learn the full dynamics using that limited set of data we have, things go terribly. We actually get about 30% success within the error threshold that we want for our task. If we have no classifier, which means we just completely trust the learned dynamics model, we do better. We get a little bit less than 60%. But the best is, of course, to use the classifier. because the classifier is going to tell you where the learned model is unreliable. And there we get a little bit less than 80, maybe 75% success. We didn't do the recovery in this sense because for the cases here, there was no need to do it. It never entered the stuck. So overall, we see the classifier boosts the success rate about 20%, which is quite significant. For the task of manipulating a rope among obstacles on a table, where we're trying to place the center of the rope in some target area, you see in green there, we tested, again, the same methods, and again, the same ranking appeared, but now we're also looking at recovery, and it turns out recovery is really important in this task here. It gets us to about 80% success. It turns out the learned recovery versus just a random recovery policy that took a random action was not, there wasn't a significant difference between them. This is probably due to there being very few examples of good recovery in the data set we've got. We may need to find more examples to train a better learned recovery method. So anyway, the idea here is that recovery is very important and highly boosts the success rate. And all of these methods vastly outperform learning the full dynamics, which is really kind of the default way to do it in the literature right. So here's an example of a demo of this rope dragging task. We're trying to place the end of the rope into the circle. As I said before, these are just demos. So these were planned in simulation, knowing the models of the real world, and then executed in the real world. We're working now on integrating that perception system I showed you earlier with this method so that we can replan given the state of the rope online. Here we're in a car engine bay and we're trying to get a hose to a certain location. You can see it's simplified a little bit. We removed a lot of the components of the engine bay, but still some nasty geometry that the rope can easily get stuck on, and definitely starting in a state where the rope is touching an object, which is going to require recovery. Here, again, avoiding a lot of the potential hooks and obstacles you see there to bring the hose ends to a certain location. Here's another example where we have straps. Let's say the engine was just installed using these straps and we have to get them out of the way. So the straps actually start under these hooks, and it's difficult to get them out of there. You can't just go in a straight line or anything. So you have to do some motion planning to get yourself out of there and then move to the goal. And again, our method is able to handle all this complex geometry and produce effective trajectory. So what did we basically talk about today? We talked about what we do when a dynamics model is unreliable, right? And though there can be many things you can try to do, improve the model and so on, one of the most important things that we think is really going to make these methods effective is no matter how good the model is, it's going to make mistakes. It's going to be unreliable somewhere. So we better know where that is, and we better learn how to avoid those mistakes or those unreliable areas, and how to recover when we do enter one of those unreliable areas. So with that, I'd like to say thank you, and to thank my awesome students in the lab who did all the work that you've seen today, and also thank our sponsors for supporting this research. Thanks.